All right, welcome back to linear, nonlinear, and mixed effects models for our last unit on correlation structure, and we're going to start with the first lecture on structured residuals across groups. So as usual, no required reading, but there is a really nice website that I got a lot of information and inspiration from and data, so feel free to check it out if you're interested or have questions. So let's go. We haven't really talked a lot about residual structures, so let's go back to thinking about constant models, really simple models. When we have models that assume independence among our data, we assume that there's a constant variance across our data and no covariance. So what that looks like is that our dependent variables y are distributed normally with the mean mu and a variance of sigma. And when you have lots of data, your sigma is large sigma here. And so what that looks like in practice is that on the diagonal, you have your variance sigma squared, and each column is a data value 1 through 5 here, and then 1 through 5 going down the rows. And then you can see there's no correlation among any of your data values, hence the 0 in all of the entries of the matrix. So let's think about this as a correlation matrix for our entire data set. Here you have your variance sigma squared for each individual along the diagonal in orange. So maybe that's there's a variance there of 0.12. And again, there's no covariance among any individuals, so the whole matrix is in gray. The rest of the matrix is in gray, and you can see we have data points 1 through n at the top, and also 1 through n for each of the rows. And what this looks like when you plot your residuals against your predicted values is that the variance is equal. And that's indicated by these red arrows that approximate the variance. You can see that they're all equal in size and that there's no trend with your predicted values. However, we can also relax the assumption of equal variance and estimate all of our variances separately. So our variance matrix in its simplest form now looks like this. So we still have no covariance among data points, but our variances are now sigma squared 1 through 5, so we can estimate them differently if we want. And what that might look like is that when you plot your residuals against our predicted values, you might see that the variance is increasing with increasing x. So you can see something's going on here. Perhaps there are groups in your data that are causing you to have different variance. So to make more complicated residual patterns, we need to think about the underlying covariance or correlation. So let's switch for a second to thinking about correlation structure. But remember, we're going to still try to think about variances as either being estimated constantly or separately. And so what we're going to do is we're going to move our variance or sigma squared outside of the matrix, and so we now have sigma squared I on the outside of our matrix. That will be multiplied by all values within the matrix, and our I, we could specify those all equally or separately. And so here our rho values, our Greek letter rho represents the residual correlation among observations. And so when we look at the diagonal, we're always going to have ones there because the correlation with any value with itself is always going to be 1. So your diagonal will always be 1. Then you have your Greek letter rows 1 through 10 to fill in the rest of the matrix. So for example, row 1 is looking at the correlation between values 1 and 2. Row 6 is looking at the correlation between values 2 and 4, and so on. And all these Greek letter rows could be equal or they could be different. It depends on the situation you have. And so this matrix is symmetric, I'll note, because you can fold it in half along the diagonal and your row values are the same on either side. So let's just think about a simple example. Imagine you have 5 measurements and each measurement is correlated to the next one in a sequence, but no others. And that correlation is equal. You might expect the correlation matrix to look something like this. So you have your sigma squared I on the outside. Again, you could still measure that separately, independently or equally. They could be equal. And your diagonals are again 1. And then in the values in the matrix where you are looking at 1 entry versus the next one, you have a correlation of 0.06, and that's the same across all your individuals. They're correlated at a 0.06 level from one individual to the next. So let's think about this in a little bit more complicated or more realistic of a case. Imagine you have 5 individuals and you have 6 measurements per individual. So you can see I have the large blocks in this figure indicated as your individuals 1 through 5, and each row and column is time 1 through 6, or repeated. So here you can see that within an individual, the correlation between their values is estimated as 0.06, but there's no covariance across individuals. And your differences in your sigma squared I across time could be multiplied by these covariances, and they could be constant or they could vary with each individual. It just depends on how you want to set this up. So let's look at an example in a data set on individual mystery snails. So it's going to look very similar to that matrix I just showed, where we're looking at the biomass consumed for each snail over the course of 6 months and their sex. So each individual is consuming biomass for a course of once a month for 6 months. And we want to find out if male or female snails consume more biomass and if this is dependent on the month sampled. So this is what the data look like. Column for individual, month as a character, biomass, sex as male or female, and then month name as character. So one way we could look at this, the way we thought about this last week, is with a mixed effects model. So you can model this with your Elmer function, biomass as a function of sex and month, with a random effect for individual, because it does seem like individuals may be different from each other, but similar across. The response could be similar, but they could have different intercept, for example. And so we model this here, and when we get our results, we see that both sex and month significantly predict the amount of biomass consumed. So what does that look like if we were to plot our mixed effects model? Here you can see that biomass consumed across months is increasing, and that the sex of the slugs also snails makes a difference. So you can see that female snails consume more biomass than male snails. But we know that there could be something going on with month, right? Month is temporally correlated, and there could be difference in variance in the amount of biomass consumed per snail across the months. Say snails just get better at figuring out how to eat biomass as the months progress, and so there's less variance. And so when we plot the residuals of biomass consumed per month, you see that there's a clear trend that there's a difference in residuals through time. So the residuals tend to have a smaller variance through time. So how do we take this into account? Right, there's clearly residual structure despite having equal correlation among individuals. So we'll need to specify our sigma squared i's differently. So we can go back to our simplified matrix that's shrunk down, where we have our diagonals of 1, and within it, individuals we have a correlation of 0.6, but we're going to have to correlate our sigma squared i's differently. And so to more appropriately deal with the correlation across time, not necessarily that there's a trend in time, but just that there, for example, autocorrelation, just that there's differences through time and through month, we can parameterize the weights argument in a mixed effects model using LME. And I'll note that this is a slightly different formatting than LME4, which we'll see in a couple slides. So unfortunately, we can't use LME4 to change our correlation structure. The way LME4 runs under the hood makes it very difficult to include weights. So when you want to account for a correlation structure, use LME. This will allow the model to estimate a different variance for each month. And there's a bunch of documentation that can help you with this. So check out this page for documentation on how to specify the weights argument, and this page for different types of classes of weights. There are a bunch of different ones. But in our case, we're going to want to use the class var ident because this allows for different variances according to the level of a classification factor. And so in our case, we have different variances per month, so that's why we're going to use var ident. So we're going to specify weights with var ident using, and you can figure out how to specify it using this page, but we'll specify our starting variance V as 1 and the grouping factor G as month. So again, notice that this is slightly different form for a mixed effects model in LME versus LME4. So just keep that in mind. But when using LME to do this, we specify biomass as a function of sex and month. Our data are snails. Our random intercept is individual, and then our weights are in this var ident in the form of 1 pipe month. And so here's what we see. Here are our results. We can see that in our variance structure, we get parameter estimates for each month. So 1 through 6, you can see that they're estimated differently. They range from 1 to about 0.34, excuse me. And then when you look at the fixed effects, you can again see that sex and month are determining the amount of biomass consumed. So here you again see that males consume less biomass than females, and that there is a positive increase in biomass consumed through time. However, you also see that there are different parameters estimated for each month, as I mentioned. And I will note that with LME, you sometimes will need to look up your p-values with a table, if you remember those. Here we would need a table of t-values, and you want the one-tailed row. Because you can see in our previous example, the p-values are not estimated with, they're just estimated as 0. So you want to make sure that you look them up so you can specify them when you report them. So for example, in our case, for sex, we have a t-value of negative 4.15 and a degree of freedom of 198. So our p-value is less than 0.0005. So we might want to estimate our residuals, right? And so with this formulation, you can get our residuals, we get our residuals in standard deviation form instead of variance. And so you can see that variance decreases per month that match the graph we saw, but the actual values are not provided. So I'll just refresh your mind of this is how you look at the variance components per month. So to get actual estimates of your residuals, which you might want, you'll want to scale them and square them to get them on the variance scale in the form of your data. So here's the code you want to use. You're probably going to have to look this up every time. And there are your estimates for each month of your actual residual variance of biomass consumed. Okay, so there are some alternatives to doing this. One alternative that's pretty new is this library GLMMTMB. And you can find out more information here. I'm definitely not an expert with this library by any means, but it looks like it could be really useful, so something to explore. And just to provide an example of how this can be useful, we're going to code our example with this library instead of LME. And I'll note that here I'm using month name for the correlation, which is a character, not a number. It seems to work out better that way. So here we have, using our GLMMTMB function, we specify again biomass as a function of sex and month, plus our random effect for individual as the random intercept. And then we use this, the diagonal function here to specify the correlation structure where we have our month and individuals within month, and then our data is snails. And I should have included the results of this. I apologize for that. Just go ahead and try it on your own. The codes here, you can see that you get a very similar significant result, but you have nice p-values. You don't have to look them up in a table. And to get your residual estimates, you can try this. This code helps you get your actual residual estimates for each month that are standardized appropriately. So again, this matches what we saw using the LME code to get the standardized variance estimates per month. Okay, and with that, we're going to be done with this lecture, so please complete quiz 7.1 on Canvas and continue on to the next lecture.